Now, when we talk about acid-base analytical chemistry, we're talking about determining how much of the hydronium ions or hydroxide ions are delivered into solution, and from that we define the relative acidity. Typically, as you're comparing one acid to another, or you're trying to define the strength of the solution you've prepared in the context of working with acid-base solution reactions. So you need a mathematical method of characterizing, well, how strong is this acid or how weak is this acid in discussing its nature. Well, one way, as you may be familiar with, is pH. Many people understand, and some experience with pH, and you've heard pH 7 neutral kind of thing, or if it's low pHs is acidic and high pHs is base. Well, that is a gauge, but there are other methods of defining acid-base strengths, not just in pH numbers, but also in other formats, indicators, pH, hydrogen and hydroxide concentrations, and so forth. So that's what I want to try to give you a good cross-section of as we go through this. Well, we start out with what is the analytical chemistry based upon? What's the most fundamental issue? And that is what we call the self-ionization of water. Now, ammonia does a self-ionization, but we'll look at that deep, probably in the next chapter more than this one. But self-ionization of water is the fundamental equation or reaction that is responsible for the existence of an acid solution or a base solution. Now, what does that mean? It means if you have two water molecules, and consider this in the Bronsted-Lowry context, one of the compound water molecules will transfer its hydrogen to the other, and will set up an equilibrium which will contain a molecule having 3 hydrogens attached to it, like this, and it will be carrying a positive charge. And then you'll have an hydroxide over here, and this, of course, is the hydronium ion. Right there. Now, this is condensed into 2 H2O in equilibrium with H3O plus OH minus. And this is the net equation for the self-ionization of water. Now, chemists are inherently looking for shortcuts, and so one that is used is the H3O. The hydronium ion is, in these problems, is usually represented just simply as an H plus and an aqueous solution plus the OH minus aqueous solution, and you have 2 H2O aqueous if you want to put it that way also. But this is the shorthand, and it is the one that's typically used when working with the acids, H's and OH's in solution. Now, when we consider this autoionization reaction, it has been shown, or you might say at this point, you are given the concentrations of the hydronium ion, and I'll call the H plus hydronium ion as we go through this, hydronium ion concentration and the hydroxide ion concentration. You're given that. So we're given the concentrations of the hydronium ion and hydroxide, and it turns out that they are 10 to the minus 7 molar each, equal, because it's a 1-to-1 ionization off of the H2O. But this is conditional. This is in pure water. So there's no excess OHs relative to hydrogen, nor is there excess hydronium ions relative to the hydroxide. So in this condition, we say the concentration of the hydronium ion concentration equals the concentration of the hydroxide ion. This is what we refer to as a neutral solution. So in pure water, a factoid is that water ionizes, and this is at 25 degrees C, so that's a standard thermodynamic temperature that we're using. 25 degrees room temperature. You can pretty much expect or depend on a water ionized to deliver 10 to the minus 7 molar in hydronium ions, 10 to the minus 7 molar in hydroxide ions. Now, this does not mean that you can't have an imbalance between the hydroxide ions and the hydronium ions. If the hydronium ions concentration is greater than the OH minus concentration, that characterizes an acidic solution. And if the hydroxides are greater than, I'll put it that way this time, greater than the hydronium ions, then that characterizes a basic solution, also known as an alkaline solution. So now we have three conditions that we need to use to, say, identify whether a solution is an acid or a base or neutral. Okay, Jonathan. Kw is defined as the ionization product constant for water. That's what it's called. And has a value, Kw equals 1.0 times 10 to the minus 14 is its numerical value. No units, just 1 times 10 to the minus 14. So where does this come from? Okay, if we look at the autoionization of water, I'll take the two. I can take the 2 off now, like that. Now, let me do this. I should put H2O as a liquid, and then H plus AQ and OH minus AQ. It'll work better. Now, I've given you 10 to the minus 7 molar and 10 to the minus 7 molar over here in these at 25 degrees centigrade. Now, what is the concentration of water over here compared to these? Well, if you watch what I do here, because this shows up in about 2 or 3 more points. If you were talking about a container of water, 10 to the minus 7 and 10 to the minus 7 would refer to, say, 1 part in, I don't know, 10 billion. So when you talk about all of the water molecules in here, maybe you have 2 or 3 that go to hydronium ions. and just a couple that go into solution and at neutral, those would be equal. Compared to the amount, this is very important, it may not mean anything now, but it will. Compare the concentrations here compared to what's left behind, unionized, the water is considered to be infinity. Now, this is a kind of a mental issue that you see this idea. Maybe one or two of these ions are floating around and everything else in the room is water, unionized water. So, the next step in this is write the equilibrium expression for the autoionization reaction as we have written it in the previous chapters. That'd be the product of the concentration of the products divided by the product of the concentration of the reactants, right? Isn't that what we've been doing? Okay, and that's called the equilibrium constant. So that would be the true equilibrium expression for the autoionization for water, as I've given you the equation up here. However, in the context of pure water, this is 10 to the minus 7 for hydrogen. OH would be a 10 to the minus 7, but the denominator is infinity. So the amount ionized doesn't change the original concentration. So if you took infinity for water minus 10 to the minus 7, what would you get? You'd still have infinity. Do you see that, please? Yeah. It's very important. So what science says is consider this to be constant. So you really didn't change the amount of water. You still get the same number compared to the amount of ions delivered. You didn't change it. That makes sense to you? Okay? Okay, so if it is a constant, you collect all the constants on the left side of the expression. So we'd move this one over here, and we would have KEQ times H2O concentration to equal hydronium ion concentration times the hydroxide ion concentration. This expression on the left is redefined as the KW of water. That's what it ultimately boils down to. And KW expression is H plus OH minus, like that. So this is the foundation equation for understanding analytical chemistry of acid-base systems. So that it is from here we will use this to work some problems and so forth and so on. Now, I'm just going to put that down here. The value of KW now can be defined, and hopefully you understand, in the following way. KW, again, is the hydronium ion concentration times the hydroxide ion concentration. And in pure water, what did we say about the concentration of each one of the ions? It's 10 to the minus 7. So you see 10 to the minus 7 times 10 to the minus 7 is 10 to the minus 14. So KW is the 1 times 10 to the minus 14 that I've shown you earlier, and you need to memorize that. And it's, of course, at 25 degrees C. If you change temperature, you will change that, but all the problems will work, except unless it's specific for temperature change, you'll use 10 to the minus 14. So that's a constant that's going to be used over and over and over again. Okay, so we're given the 0.25 molar HCl. Is HCl a strong acid? Yeah, so it's going to ionize 100%. So 0.25 molar HCl will deliver 0.25 molar and the hydronium ions plus 0.25 molar and the chloride ions. Because it's 100% ionized. It's 1-to-1. Everybody good so far? Good. This is then placed into the Kw expression and solved for the unknown hydroxide. So from the fact that this is a strong acid, we've answered the hydronium ion concentration. So just looking at this, it might seem kind of, well, it's obvious. Well, if this is a strong acid, yeah, it's obvious. Now, when you get to weak acid, it won't be obvious. You won't have you can't just say it's 0.25 for, say, 0.25 acetic acid. It doesn't work. I'll show you it's a simple step. So now, we've answered A choice, problem A. Now we're going to get the hydroxide. Well, you use the Kw expression. So you come down here, Kw equals hydronium ions, have the hydroxide, and you solve for the hydroxide and plug in the numbers. That's all it is to it. So our OH concentration now is 1 times 10 to the minus 14. See, we're using that Kw number. And the hydronium ion was determined to be 0.25, and this will all come out in moles per liter. Now, I would strongly suggest, if you need to, pull out your owner manual on your calculator and become very proficient with exponential notations and converting to exponential notations, because we're going to be using a lot of it throughout the remainder of this section. Since this is the hydroxide and this is the hydronium ion, we clearly see hydronium ion, which equals 0.25 molar, is much greater than the hydroxide ion concentration, which is 4 times 10 to the minus 14 molar. So this is clearly an acidic solution. Because of what I showed you earlier, how do you define the acid solution? Well, the hydronium ion's got to be bigger than the hydroxide ion concentration. So we note that we're working with a 0.33 molar sodium hydroxide, and sodium is a group 1 metal. And so group 1 hydroxides are strong bases. So we have a 0.33 molar sodium hydroxide will go to a 0.33 molar in sodium ions and 0.33 molar in hydroxide ions. As a strong electrolyte, ionizes 100%. So from this, we can directly read the hydroxide ion concentration is 0.33 molar. And so that takes care of the the hydroxide concentration in the problem. Now we need the hydronium ion concentration. Well, you will use the Kw expression for water, substitute the OH and the Kw and solve for H.
Yeah, you told me. Dr. Palezzo? Doctor?
Duh. And I get 3.03 times 10 to the minus 1 molar. Right there. So in the comparison world, this is clearly an alkaline solution or basic solution. For the most part in student lives, is I'm guessing, your exposure to this concept has been pH. But know that there is pOH as well as pKa's, pKb's, pKsp, and on and on. Well, where does that come from? When we talk about pH and pOH, it is based upon what we call a p-factor analysis. And the p-factor is, in this case, hydronium ion concentration or the hydroxide ion concentration and so forth. And its purpose is to put very small numbers into a more convenient form. And that's all it is. So that gives you a kind of a quick definition of why it is used. Well, the formula for pH and pOH and P whatever is a simple one, and we call this P factor, say Px, where the X is the X factor. And X can be the hydroxide or the hydronium or whatever you're working with. And it turns out simply to be a minus log, common log, of whatever the molar concentration of that X factor or number is. So it's very easy calculation. So if something's asking for hydronium ion concentration or a pH, you first have to get the hydronium ion concentration and take the minus log of it. And if they're asking for the pOH, then you would have to take the minus log of the OH concentration. That's what it refers to. So let's say you're given hydronium ion concentration to equal 1.25 times 10 to the minus 3 molar in aqueous solution. What's the pH of that solution? So simply pH is equal to the minus log of the factor that you're interested in, and that factor H is the X factor. And so we substitute 1.25 to 10 to the minus 3 into the concentration point. It's minus log 1.25 times 10 to the minus 3. And we'll punch that in the calculator. And just hit the log button. It will come out as a minus 2.9. Just leave it at that, 2.9. I forgot the negative. Minus a minus 2.9. Notice I left the 9 in here because when you take the logarithm of a fraction, a decimal fraction, it's going to come out negative. So you wind up with a negative times a negative, and this ultimately goes to 2.9. So the pH of a solution with 1.25 × 10 to the minus 3 molar in hydronium ions is 2.9. See what I'm saying? Same way with hydroxides. If you're given an hydroxide ion concentration to equal 0.318 molar, then what's the pOH? Well, the X factor is whatever that OH concentration is, minus log of the hydroxide, and you plug it in, hit your log button. Now, it's pretty straightforward in some calculators. I'll show you real quick. Let me move that up here. So that's minus log 0.318, like that, and then we'll get a minus something. Now, let me show you. Okay, 0.318. Okay, so what I'm doing is I'm putting in the 318 in here, and you might have gone through a calculation and gotten the hydroxide ion concentration here. All I'm doing is going to come up here and hit the log button, like that. And then that gives me a minus 0.5. We'll round it up to a 0.5. So I have so what goes in the parentheses in here is a minus 0.5, and so that is 0.5 is your pOH number. And so you practice that so it'll be easy for you on test day. You won't have to go fumbling around trying to figure out how to get the exponentials in there. Well, there is a very simple relationship between pH and pOH, and it turns out that pH, and you'll use this more than you will use what I just showed you, pH plus pOH always equals 14. So these are exponentials. If you had the 10 to the x plus 10 to the y, you would have 10 to the x plus y. Well, pH and pOH are logarithms. Well, logarithms are exponents. So as an exponential, it is x plus y equals x plus y over here. And it's just a beautiful formula, and it may not mean anything to you right at the moment, but what this eliminates is you having to go through determining the OH to individual concentrations and apply it to the KW expression, and then go back and do the pH expression. You don't have to go that. It works, but once you get the OH, you just hit the log button and then subtract 14. So it's a shortcut that everybody uses. I mean, once you learn it, you'll always use it. So what do we do first? One is examine the acid that you have in the problem and determine if it's a strong acid or weak acid. Well, we haven't dealt with any weak acids so far, so you should recognize now that that is a strong acid, which means you should say 100% ionization. So if we have a 2.03 times 10 to the minus 3 molar HBr, then it's going to deliver 2.03 times 10 to the minus 3 molar in hydronium ions plus 2.03 times 10 to the minus 3 molar in bromides, which would go there. Now the bromide is a spectator in all this. Our primary concern is this. So from this ionization, we can simply say the hydronium ion is 2.03 times 10 to the minus 3 molar. So now the next question is, what is the hydroxide ion concentration? Well, how do you get that? Now you go, all right, now listen to this. Since it is a strong acid, you can go direct to the KW expression for water. When we get to weak acids, there's a step between the KW, between the acid, the hydronium ion, and the KW expression, and we'll show you there when we get there. But anyway, from KW equals H times OH, we get OH equal KW over hydronium ion concentration, like that. And of course that is 1 times 10 to the minus 14 over 2.03 times 10 to the minus 3. Everything comes out in a little better moles per liter. And so I get 4.9 times 10 to the minus 12 molar in hydroxide ions, like that. So the next issue is, what is the pH and pOH of the system? We'll do the pH first. So the pH, of course, is minus log of the hydronium ion concentration, which is simply minus log of, what did we come up with? 2.03. 3. You don't even have to put the units in because the pH doesn't have units. And we have 2.03 times 10 to the minus 3. It's a log, but I got 2.7. Okay. So everybody pretty much see, it's going to come out, let me make an emphasis, that. Minus a minus, and you know it's going to go positive. So I just punch it in. If it shows negative on the calculator, I know it, just change the sign, because it's going to be positive anyway. So the next one is the pOH of this. Now the pOH can be calculated as minus log of whatever its X factor is, and that would be your molar concentration of the hydroxide. Now there are two approaches to this. One, you can go back up here to the acid concentration that you have. Well, we already got the OH concentration, didn't we? Take that OH concentration and calculate the pOH from that. So using that, it's minus log of 4.9 times 10 to the negative 12. And so in this, using the concentration there, 4.9 to 10 minus 1,2 log, I get 11.3 is the pOH. Now that is not corresponding to pH. It's opposite. So if you wanted to talk about an acidic system, is something with a pOH of 11.3, acid or base. Don't get that mixed up with pH. A pOH of 11.3 is a very acidic system, because we just showed that up here. pOH is a different number. Now notice what the outcome of these are. All I did was take a small number and put it into some kind of reference number that's a little easier to deal with. That's all it boils down to. Chemists are inherently lazy like me. And so I want it in something I can just glance at and say, oh, that's an acid system, below 7. But I can't say pOH. Now, if I had a pH at 11, yeah, that's great, man. You know, that's a base. So you recognize that. Okay. Or, in this problem, let's say you have the 2.7, pH 2.7, then you can use pH plus pOH is equal to 14, where pOH is equal to 14 minus the pH, and therefore pOH now is 14 minus the 2.7, which will also give you that 11.3. And there will be cases where that'll be a lot more convenient than trying to go back and recalculate your hydroxide ion concentration from the KW expression. And you just, once you get the hydrogen, you can get the POH the OH very easily, or the POH just by subtracting it from 14, the pH from 14. Okay. Weak acid, weak base, analytical. So when we use analytical methods for evaluation of weak electrolytes, so weak acids and weak bases, we want to take into account, say, determine hydronium ion concentration, the hydroxide ion concentration, pH and POH, of a 0.25 molar acidic acid solution and water. Now, so step one is to look at the acid you're dealing with or the base you're dealing with and decide whether it's a strong or weak system. If it's a strong, one of the strong electrolytes, then you can ionize 100% and one of the ions is available. And then you plug it into the KW expression. But that doesn't happen with compounds like acetic acid, boric acid, and on and on and on. So we look at HOAC ionization, and it is an equilibrium that's delivering hydronium ions and the acetate ion into solution. We're given that we have 0.25 molar in this compound in solution, but what can we say about how much the hydronium ion and acetate? They'll be in equal amounts because they're one-to-one ionization. Can we say that they're 0.25 molar?
No.
No, because the ionization is less than 100%. So you have not just the ions in solution, but you also have molecular forms floating around the solution. So what do you have to do? Well, there's a simple formula when working with weak acids to determine the hydronium ion. Or if you're working with weak base, there's a simple formula for determining the hydroxide ion concentration. That formula is, and then we'll develop it next time, or when we get into the next chapter, the hydronium ion is the square root of the Ka value for the acid or base under consideration times the acid concentration, and it is expressed in moles per liter. And we'll show you how this evolves out of the ice table when we get to the formal presentation of weak electrolyte. So in this particular case, the hydronium ion, now the Ka value is the acid ionization constant, and it'll be given to you. So we have a Ka equals 1.8 times 10 to the minus 5. That's a given. Along with whatever concentration the acid is. And you just simply plug and chug. 1.8 times 10 to the minus 5 times 0.25 square root of, and it will come out in moles per liter. And that gives us 0.0021 molar in hydronium ions. like that. At this point, once you get the hydronium ions, yes, now you go to the Kw expression. And then solve for the hydroxide ion concentration if that's what the problem is asking you for. So, everybody see that? 4.76 times 10 to the minus 12 and hydroxide ion in that. So once you get this far, then you go into the pH and POH just using the XP factor equation, and you finish that problem. So given the hydronium ion and the hydroxide, we can simply get pH to equal minus log the hydronium ion minus log of 0.0021 and I get 2.7. That's good enough. Now, two ways to calculate the POH. You can use the hydroxide ion concentration we calculated above, which is 4.76 times 10 to the minus 12. That comes down from up here. I get 11.3. Now, you can add these two together and you can see that the pH plus POH gives you 14. If it doesn't, you might want to roll back and make sure you push the right button on your calculator. I have on the past pushed the LN button instead of the LOG button, so causes confusion. But if you get to the 2.7, you can go to POH equals 14 minus the pH, of course, just like we were showing here, 14 minus 2.7 to give the 11.3. And so that shows you how that is a shortcut, so you don't have to really go through writing down that calculation in that way. Given a weak base, ammonia, we have 0.175 molar ammonia aqueous. Now, to understand that ammonia is the weak base, but the chemistry evolves off the ammonium hydroxide. But when you read the textbook and problems that come to you on test day, they'll say which of the following is a weak base, and they're not going to put an ammonium hydroxide, they'll put an ammonia there or an ammonia derivative. And so you pick that one for the weak base. But when you go into the calculations, yeah, it's an hydroxide type system, because NH3 plus H2O will go to NH4OH. You see the hydrogen's absorbed by the ammonia. One of the water hydrogens is absorbed by the ammonia. And we get the ammonium ion plus the hydroxide ion, and that's the one we're trying to calculate, the hydroxide out of that ionization. But while this is a 0.175 molar in the ammonia, it is also 0.175 molar in the hydronium ion. But you cannot say the hydroxide or the ammonium ion is 0.175 molar, because it's a weak electrolyte and does not ionize 100%. But to get the OH, it's the same kind of formula. But this time you'll use a Kb value times whatever that weak base concentration is, solve for the OH, and then you go to the Kw expression or go to 14 minus the POH that you get. Anyway, Kb for ammonium hydroxide, 1.75 times 10 to the minus 5. So that would be the square root of 1.75 times 10 to the minus 5. And we chose 0.175 molar. And the finished answer will be in moles per liter. So you're 0.00175 molar in hydroxide ions. So we can just punch the log button. See, I'm already at, have that in my calculator. So if I want the POH, I just hit the log button and remember that it is going to convert to positive, and this is 2.76. And then if I want the pH now, it's 14 minus POH, 14 minus 2.76, and so I will minus, and I will just simply add 1/4 to that, and I get 11.24. So you can see there's a lot of little shortcuts. Once you get acclimated to this, everything just flows real nicely, but you must practice it. Just pick you an acid, pick you a base, and make up your own concentrations, and then go through it. You'll look up the Kas and Kbs in the next chapter. The beginning of the next chapter has tables for that. As a matter of fact, I will have a Ka, Kb attached to the test. That's something you normally look at. Or if most of the problems will have the Kb embedded in the problem, or Ka, or whatever you need. Okay, we started off in here and developed, went through the auto-ionization of water, and we find that water will ionize to a fundamental amount in pure water with a Kw equal 1 times 10 to the minus 14. Now, one of the things you want to note here is this is 10 to the minus 7. This is standard, 10 to the minus 7 at 25 degrees C. And that is the foundation for the Kw expression of H plus times OH minus. Then we defined what an acid is and a base is. If H plus is greater than the hydroxide concentration, then we call that an acidic system. If they're equal, there's neutral. If the hydroxide is greater than the hydronium ion, then it's an alkaline or basic system. Like this. And so the objectives and problems that you will be working, you'll be given a concentration of compound, and you're asked to calculate hydronium ion concentration, or determine OH concentrations, pH, and POH. So using the KW expression for those, and then you use the P factor for those two. If you can see all the scribble in there, if that makes any sense, I can clean that up some. Whatever that X factor is in there. So, now this is a direct relationship in analysis of strong acids and bases go direct to KW equals H plus times OH. Is paraphrased there, but yeah, I think you understand what I'm saying, because the strong electrolytes ionize, and you will have one or the other from the strong base or strong acid ionization, OH or H. But in the analysis of weak acids and bases, you first have to calculate the hydronium ion if it's an acid, using the square root of Ka onto the acid concentration. That's step one. Then go to the KWH times OH. Same way with hydroxides for bases. It's a Kb number, and that's given. Then go to the KW expression. Okay, so you have to keep all this sorted out in your mind. It's not that difficult when you start working these problems. You extract the data out of the problem and decide first if it's a strong or weak acid. And then you follow the protocol for the strong acid. You can go straight to the KW because one of the ions is going to be known from the ionization. But if it's a weak electrolyte, you have to apply the square root formulas and then go to the KW expressions.